Welcome everyone to the AI Research Bites. This series of short and informative talks showcase cutting-edge research work from ServiceNow AI Research. The AI Research Bites are open to all, especially those interested in keeping up with the fast-paced AI research community. Today's session features a 15-minute talk from Sai Mudumba on recent work on enabling builder and creator agents on websites. Sai is a research scientist at ServiceNow and an adjunct professor at Université de Montréal. He holds a PhD from UDM Milan and has been super active in multimodal AI research. He's also been super generous in sharing his insight with us at the AI Research Bites, so make sure to check out his previous presentations. Up to you, Sai.
Yeah, thanks for the kind introduction, Fanny. Always a pleasure to be here. Since I'm here, if anyone of you have listened to my previous presentations, it's obvious that there should be some multimodal content in it. And of course, we'll be talking about a multimodal and this time multilingual evaluation of agent reasoning on web. Our WebMMU paper, which has got super positive reviews in EMNLP. And it's essential need of the hour that we'll be presenting and talking about this work. So without any further delay, let's quickly move to the content of the talk, the timeline. So we will be starting with a quick intro slide on why we need more benchmarks like WebMMU. And then what exactly is WebMMU? What is it composed of? And then we'll talk about the evaluation framework itself, and then some sort of takeaways that we should be taking up, maybe one or two, not more than that. If essentially what should we be taking home from this presentation, right? So without any further delay, let's move to first a very quick motivation of why we need benchmarks like this. So there are pretty much already pretty fantastic benchmarks out there in websites. So web agents that are powered by large language models are also pretty smart in given user instructions. They can browse the web for you to solve a task conditioned on the instruction. They can click and type on the screen to solve the task or a number of feasible steps, right? But the problem is they sometimes use backend code, and sometimes they also use computer vision or web screenshots to navigate or solve the task. But they can hardly reason over a complex web page visually most of the time. And even hardly they cannot really code or fix or repair or edit a web page itself, provided an instruction from the user. So this, what I mean to say is that the web browsing or the task solving is just one piece of puzzle of this bigger chunk of what we can do on web, on design, build, maintenance kind of cycle. Web browsing comes as a tiny part, and most of the web benchmarks evaluate on this little part, while sort of ignoring on the bigger chunk that can truly decide whether the agents are autonomous or intelligent or not. So uh, in this bigger cycle, so we truly can consider an agent truly autonomous if they can actually do three things or a bit more, depending on how we see this. If they can see and reason on the website, if you can see the website, which is like multimodal in nature, and they can do some sort of complex reasoning on top of that, is one desired data. The second thing is, can they read people's, or they can actually create the website itself from the get-go, from the intent, from sketches, from mock-ups, from sort of a wireframes. Can they create the whole code? Can they the website to its true form? The third thing that is desired is that can they, given a website and user instruction of how it should be or what needs to be fixed, can the agent evolve, adapt, and fix the website or change the website to a form that is desired? That is, it produces some sort of a diff code kind of a thing that can adhere to users' instructions. Right? Why should we be measuring all these three things instead of just task solving on web? Because are they necessary to improve the current web agents? Maybe not. But having this sort of a fine-grained, granular understanding of both the front end and back end code of the website would allow users like me to trust the web agents or agents with my credit card, for example, to buy something on the web. I think the whole idea is that can we measure, evaluate, and improve these agents on a complete level rather than just one narrow domain to make them truly autonomous and then solve the task. And particularly for enterprises like ServiceNow or Salesforce, this is very more important because we prefer low code kind of a paradigm. So if the agents can create the code, fix the code, adapt and reason through the code on the website code instead of just solving in addition to solving, then I think it's even more better. So this is the whole motivation of like why WebMMU is there. So with this, let's move to like what are some sort of key features of this evaluation framework itself of websites, right? So it's a very, as I mentioned, it's a holistic benchmark. It has three components. One is if it can, see and reason, which is like it dealt in the form of question answering, web question answering and action-based question answering, very complex based on the visual cues alone. The second aspect which we evaluate is code editing or code fixing or repair. So given user instruction, given a web page, can you modify the code, the web code itself, so that it can come up with some, it can solve or you can come up with a desired code difference that can provide the user requested features into the web page. The third thing is design to code. Can given a design, hand-drawn designs or some sort of conceptual designs, can it generate the whole website by itself? So that, which means that the more you, if the agent can actually create, or if it can understand the creation process, then it may be able to like understand different aspects of the website, so it can actually do other things even better. So it's a unified benchmark. That's pretty one. And second is on our biggest more important thing is that it's very close to real world. We want to make sure that people across the world try to use it for realistic scenarios. So it's multilingual in nature. First, multilingual visual web in nature. So we cover currently 4 languages. Spanish, German, French, done by the web pages are rendered natively in the native languages without any translation. And the total items end up at more than 4,000 web pages with all the artifacts combined in across these 4 languages, which is pretty comprehensive for the current standard. And it is done by expert annotators who are trained in linguistics, at the same time computer science, to create this high quality data construction. So where we sample the web pages on different categories, at least 6 categories, like documents, education, social, and enterprise, and different sectors, and then across different languages, and make sure that there's a high filtering threshold so that we get high quality annotations and the web pages at the end of the day. So this is like the broad overview of what the benchmark would contain. With this, let's see part by part each of the things. So what do we mean by web question answering, code editing, design to code? That should give you like a good understanding of the benchmark aspects. So the first dimension is website VQ understanding. So given a visual website screenshot, does the agent how much does it understand page itself in terms of its general understanding of the image, which is like semantics and visual comprehension, like given, so what is the text present there, and where is certain image, or what exactly is the image consists of? These are the questions that you would see in general image understanding. The second thing is on function, or based on more functionality, which means that does agent answer questions very detailed fashion on how it where should it be clicking and perform and writing to perform a given task. For example, given a web page, the functionality based question answering could be something like, how can I access a stock summary of June 2024 from the web page, where the web page is extremely crammed in terms of content to make it a complex website. And then it has to figure out exactly, move to this segment of the web page. Now click on this particular thing to get the drop down. And then this region has the exact button, which at this coordinate in XYZ coordinates, that user should be clicking to access the stock summary of June 2024. So the question and answers are very detailed, done by both the authors and the annotators, to make sure that it has the exact, clear, and unambiguous steps of how do you solve a particular task. And then there is complex reasoning, which is like which is not many agents are very good at doing this. It's given a complex visual screenshot of a website, then can an agent perform like a multi-step logical reasoning on top of that? Like, for example, according to the data provided on the screenshot, if an investor bought some shares in some week, what is the total profit percentage return if he sold it in a subsequent week? And the agent has to really understand where it needs to be looking at on the whole website screenshot, then go and um, find the right information to calculate and give the reasoned thinking traces or think answers to the user. So this is an example of how complex thing looks like. And we make sure to make sure that across these grounds, we evaluate agents on these fronts. And you will see in the results that both on the functional side and the complex reasoning, the current state-of-the-art agents are extremely underperforming. The second aspect of the evaluation is given a sketch or a design of a website, can the agent code up a website from get-go, from scratch? And we can give very simplistic sketches to very detailed sketches, depending on the granularity of the details. And the task involves predicting or generating HTML, CSS backend code from these sketches or designs or wireframes. And the third component of evaluation is code editing. So, for example, the user gives the agent is given an instruction, a screenshot of the website, and the source HTML or the website code. Then the task is the agent to come up with a diff code or a difference code that actually that actually performs the change that the user wants in the instruction. This is extremely important task for a web agent or like any agent that actually can trespass or like navigate the web, because doing this is like a mass language modeling, but with a different flavor. It makes sure that the agent has the contextual understanding it requires to solve a given task. It understands in and out the front end and back end. So it knows exactly where to go. Given an instruction, it needs to first identify where the editing needs to be performed and then perform the actual edit and make sure that edit renders. So this is the third task. So these are the three dimensions the benchmark is composed of. And all the three are done for different languages. So that's pretty much is what WebMMU is. And with this sort of understanding, I would want to quickly walk you through some sort of nice analysis on the current plight of agents on this comprehensive benchmark, which is sort of eye-opening even for us when we wrote the paper and did the experiments on our side. First, the performance is on the question answering, the website understanding performance, the first segment. And the bar plot here has different performance of different state-of-the-art models, multimodal models like Gemini 2.0, Claude, InternVL, GwenVL, whatnot. And the blue bar color represents the general image understanding performance. And the green is complex reasoning, and the red one is functional or agentic action-based question answers. And even the top class, the general trend is that the general image understanding is easier than complex, whereas the action grounding or the functional aspects is the hardest part, and the models don't really get it, which is concerning because if they don't understand the functional aspects, then these models might not be yet ready to solve the complex tasks that user wants on the websites, which is very desired data that you would want to nail in the first case. Even the state-of-the-art models, for example, the closed source models do not do more than 20% on the functional, but for the complex, they get to the bulk. The best performance is just above 50%. And for general image understanding, it's slightly above 60%, which leaves a lot of room to improve here on all these segments. And when it comes to code editing, we use across all the metrics that we tried, we found LLM as a judge metric as something very useful. It gives like sort of a real world outcome feeling when you evaluate the model. So what you give is you give to the judge LLM the screenshot, the predicted diff code, and the source code and the instruction, and it has to evaluate on a couple of fronts. Is functional? Is it okay? Is it not? Is the website rendering after this? So there are 3 or 4 desired data that you average on to get this scores. And we can see that the top performing model is GPT-4 at that time, and it's even below 4 out of 5. It's reaches 3.9, and for the open source models, nothing takes off more than 2.5 or 3. So, which means that we are at a very nascent stage in this code editing performance which needs to be improved. So we made the task even simpler to get to 3.5 or 3.9 the LLM as a JET score. where we actually gave the model that they don't have to predict where the editing needs to be done, but they just have to predict the diff code. So we give the clue that, this is where the editing needs to be done. Can you provide that? So if we also ask the model to predict the where it needs to be, where the editing needs to be done, it even performs even worse, which we mentioned in the paper at some in the appendix. And the last is like mockup or design to website code, which is given a mockup or like a image of a sketch or like a wireframe, can you generate the original page itself? Now LLM again, evaluation has three things, like it scores on alignment, layout, spacing, and overall score that is averaged across these three. And the results, which we comprehensively describe in the paper, saying that the best performing model itself struggles to reach a score of 3.5. And even the best model is under 3 overall, which means that it's subjective to the one level, but we make sure that the LLM as a jet score correlates with human evaluation to make sure that LLM and the human, what the human desires to rate these models is sort of is correlated. So it's the threshold is bar enough that it's 95% of the time it correlates with the human result. So even with that, these scores, it leaves a lot of headroom to improve on this performance. So this is the state of the affairs on this benchmark currently. And we tend to, it's been a few months. We need to see where the current upcoming models are evaluated on this, friends. Just to give you a final takeaways or final summary of the gist of the whole paper, which makes you to go back to the paper and read the paper, is that if there's one takeaway, the first takeaway is that it's what I always tell the students or tell the community. I try to sort of emphasize is that we need more and more high quality evals and benchmark data. There's a critical need, precisely because there's a way ahead headroom to improve the models to solve harder problems. These benchmarks, the more harder benchmarks, high quality benchmarks that we come up with, it lets us get to one next step towards general intelligence. The second thing is that we need to avoid overly descriptive problems to generalize even a bit more to get close to true intelligence. So the high quality benchmarks, like WebMMU, can get some feel of what a generalization beyond the current pre-specified synthetic benchmarks would look like. Other thing is that we need to be chasing more and more reasoning than just true knowledge. Because if we saw even in the web QA performance, the complex reasoning and functional reasoning performance is way low compared to the knowledge-based or like semantics or things like that. So the benchmarks, we need to have more, and more should be testing reasoning aspects of things, right? That's the first thing that motivated us to take up this challenge and put out this study. The second key takeaway is essentially is the summary of WebMMU. The benchmark it proves the point that the current agents need both perception and structure to sort of solve complex tasks on web. The more holistically they are evaluated and improved, the better and reliable they can get to solving real world tasks. And WebMMU adds a range of complex tasks across domains, across languages, to make sure that it's accessible to unlock new capabilities on the web domain. And of course, there are some upcoming things on the web to make sure that we do a phased release of the website and add more languages or increase dynamism and so on and so forth. That's pretty much the work about, and I would like to thank my collaborators and students for leading this work, particularly the Rabiul, Masa, and Arash and Jichav, everybody here. It a big collaboration across different universities and annotation company. And if you want to, there's one picture that you want to take out of this presentation is this QR code that leaves you where the code is, where the data set is, who are part of it, what exactly it contains. So if you need more details, just make sure that this QR code is all that you need to know more. Thanks everyone.